Welcome, everybody. I guess you can all see me as well. Well, we have a very, very selected group of people here in person, and a very selected group of people, a bit less selected online. So welcome to this seminar. Well, the idea of this was to basically be a first event for the UK section, even though, actually for the London student section, even though we have participants from outside London, because as you know, we're trying to recreate a little bit of the London student AES section. And so we have a couple of PhD students from my team here, and then William from Birmingham, talking about different topics. The first two are going to focus on spatial audio, and the third one on violin and musical instruments, interfaces, and other things like that. So hopefully it's going to be fun. Actually, I'm sure it's going to be fun. If you want to ask questions remotely, we are a small number, so you can write something in the chat. There is a Q&A box, and you can use that. But I have to say, we are a small number of people, so you can also tell me, I would like to ask this question by voice, and I can switch you on, and actually it works quite well. So we can try like that. What do you prefer, presenters? Do you prefer questions after presentation? Yes? Okay. Yeah. Well, then let's start with the two spatial acoustics, spatial audio presentation. The first one, we have Rapolas Daugintis from here, Imperial.
Hello, everyone. Welcome to my talk. Thank you for coming. I'm Rapolas. I'm a PhD, kind of almost already doctor, kind of. I guess I just defended my thesis a month ago. This presentation is like some work that I did for my PhD. And it's about analysis of numerical and perceptual analysis of head-related transfer functions. So first of all, just a second. When we talk about immersive audio or spatial audio or so on, just to get everyone on the same background, we talk about audio that has some directional characteristics, that you hear some directionality of where the sounds come from. It can be maybe over loudspeakers, but it can also be over headphones if we replicate the way the sound interacts with the human head. And so this specifically, that's part of the binaural spatial audio research has been also a big part of this Sonicom project that I've also been involved, that's finishing next year. And so the way, of course, we understand that the sound comes from a specific direction is by analyzing, or our human auditory system analyzes the way that sound interacts with the ear, the head, and the torso, and so on. And all of these cues are embedded in what we call head-related transfer functions. They are kind of divided into binaural cues, so they are kind of level and time differences. When the sound source is somewhere on the side, you have a time delay and level difference that helps you resolve this a lateral direction. But also you have spectral cues that's notches and peaks that are related to the reflections from the ear and shoulders that help you resolve the elevation and front-back confusion, and understand whether the sound came from the front or from the back. These really depend on individual morphology of the ears. And so each of us, over the course of our lifetimes, have learned to understand our own cues and localize the sounds around us. So when we want to reproduce this, we can measure this effect or this filter in a lab like this by placing microphones in the ears and measuring the impulse responses, and then reproduce the sound by just convolving the monophonic anechoic sound source with the filter to get that spatial audio illusion, let's say. I guess, of course, it's impractical in large scale to have everyone measured. So most of the time you use non-individual HRTFs. that might not match well with you and might not have the best sort of spatial auditory image for you. So then there's all these attempts to sort of personalize the HRTFs without measuring them, and usually it involves some sort of a matching of a non-individual HRTF to individual one, and it could be divided maybe in main two categories of ways of doing it that I'll talk about. But the important thing up here is the question is, what is the close match? Because that's kind of sort of a non-trivial system. So on the one hand, you can kind of base it perceptually. So you have some sort of listening test. You ask people to say what sounds better. It really tells you what they think. And I think this is what, for example, is implemented in PlayStation 5. You can kind of select which sounds better based on this angle, I think, or height. But the problem in this approach is that it's quite so apart from, unless you sort of simplify it like in this commercial product, to get the true answer, I guess it's quite a long process because there's so many directions of HRTFs, there's so many HRTFs, and then the question is also whether how consistent the results become when you ask sort of, especially naive listeners, to do this task multiple times. They might actually give you different results. On the other hand, you can do this numerically, like for example this AirPods Pro that claim to kind of take a photo of your ear and match somehow the HRTF based on some ear features they extracted from the photo, and that can be automated. But then the question still remains on what's the perceptual submetric between the features that are taken by the photo and the actual performance of a listener in the real sort of listening situation. So so just to summarize this idea is that basically when we think about HRTFs, we have this sort of a duality of that concept. So on the one hand, they're just numerical filters that have some spectral characteristics or some phase characteristics, differences and so on. But then on the other hand, they're actually perceptual constructs in the way they only are valid within the domain of listening. But how to link the two is sometimes not easy and unsure. So I tried to investigate this sort of connection between how well the HRTFs match numerically and how much that relates to then perceptual matching or perceptual performance. And to do that, I used this. Yeah, it didn't produce a good image, but I used this auditory model, which tries to sort of replicate a human listener by sort of estimating all this spatial hearing features from the individual HRTF and compare them to sort of the incoming sound. The features embedded into incoming sound, and it does it in this Bayesian, using Bayesian inference to sort of output a localization response that would be comparable to a real human listener doing a localization test. And so I used this model that was developed by a colleague, Roberto Baromelli, and it's available in Auditory Modeling Toolbox. And then I kind of created a way to selecting an HRTF, selecting a very well-fitting HRTF and badly fitting HRTF. This figure is very difficult to see, but it doesn't really matter because within this general background, I hope to publish this figure in the paper soon, so then it will be available to analyze more. But basically, the main thing is to have one well-fitting HRTF and one badly fitting HRTF, and understand how, then use them to understand when that sort of performance difference is apparent in the listening experiment. So then I proceeded with doing a perceptual evaluation. I kind of developed a few experiments in the sort of virtual reality mainly. And for that, we needed HRTFs. So we have a lab here where we did HRTF measurements for this Sonicom project. So they're available from our website for anyone freely to use and abuse. And so then I had some participants that had their individual HRTFs measured so that I compared them with these matching or non-matching HRTFs. So then the tests were firstly a static sound localization test, so a quite classic one where you hear a sound source and then you have to point and then sort of indicate the direction of the sound that you perceive. And then there was a more qualitative test where you had to rate difference between the individual HRTF and these non-individual HRTFs using a few different qualitative attributes. So I'll just show some results that I had. So I was, as expected, I found that indeed there is a difference between sort of well-matched and poorly matched HRTFs. So there's some sort of something that the auditory model picks and matches to then lead to actually better localization or worse localization. So in this case, this is a sort of a general error of this overall distance between the responses and the target positions. And we can see that with the individual one, we have the lowest sort of average error. And then with the best, we have a slightly higher, but non-significant actually. And then with the worst, we have a significantly increased error. Also on the polar domain, we also see the same pattern. So if you only look in the sort of the polar angle, so that means basically elevation. And then also maybe interestingly kind of to analyze is a sort of how much of that error is sort of falling within the general region of the sound target, and how much of it is confused. So I could see that for individual and actually in best one, we have basically 80% of positions were kind of understood as being within that sort of general region from the target. Whereas with the worst HRTF, we had quite a lot of confusions that actually that fell sort of mainly in this sort of gray area, so front, back, and top down confusions combined. Here. And then in terms of the qualitative test, I saw that also qualitatively people perceived, although they perceived that the best HRTF as being significantly different from individual in sort of qualitative terms, the difference between the worst and individual was significantly larger. We did some statistical mixed effects models here to prove that. There was the test was run using different sound stimuli, and it's quite consistent across stimuli. Although there's some differences when you qualitative rate qualitatively broadband noise, you usually have a bit more sensitivity than when you do things with more speech or music samples. And then I could see that also this poorly matching HRTF also was associated with a higher perceived difference in coloration. Interestingly, in this case, it happened to be sort of more bright, perceived as more bright, whereas the best HRTF was sort of sometimes more darker, sometimes brighter, but around the same sort of basically kind of centered around zero difference. We also asked for ratings on more sort of higher level qualities like externalization. And although we didn't find any significant, so statistical analysis didn't reveal any significance in these results, but there's some pattern that the worst potential could be more internalized. But the problem here is that the test was also quite anechoic. It didn't have a reverb, and it didn't have it wasn't very realistic and ecologically valid. So I think questions like externalization can be quite difficult to assess in these contexts. And then I have this other study that I did that maybe I'll talk briefly depending on time. I also did this other test where I was interested in how this fitting of an HRTF affects the speech intelligibility. So if you imagine a sort of a more realistic teleconferencing scenario, let's say, and you have a room acoustics. In fact, in this test, it was the room acoustics of this room recreated binaurally. And when you have to understand the speaker in a sort of in a babble of the law of other speakers, is there any benefit when the HRTFs used as individual? Interestingly, in this case, we didn't see a big effect of HRTF condition. Here, it's basically how correct the responses were, and this is kind of when the mass hairs were in a different position than the target, and here it was when they were co-located, so that's much harder condition. And so, of course, when the harder condition, it was harder, and we saw quite an interesting result on the reverberation, because I used this quite a sort of a basic condition where it was kind of a mono reverb, and then a fully spatialized reverb based on eigenmic recording of a spatial room impulse response. And so I could see that the spatialization of reverb did help to understand the speech, but the conditions of HRTF didn't matter significantly. And we think it's there's a lot of many factors that affect in this kind of task, where even the sort of the signal level differences between HRTFs might matter more than sort of specific personalization. So it's kind of hard to assess the effect of personalization on top of everything else that happens when you try to perceive speech. So in summary, I have shown that this auditory model, specifically Birmingham 2023 from Auditory Modeling Toolbox, is able to predict the quality of the HRTF match, and that well-matched HRTFs can achieve localization performance that is comparable to individual HRTF, just slightly maybe increased error, while poorly matched do degrade significantly the localization accuracy. So there's something about matching the cues. And qualitative ratings, interestingly, also align with this localization prediction. So people perceive those HRTFs as being more perceptually different, while the speech intelligibility has sort of other factors in the binauralization whole rendering pipeline that probably matter more than specific match of an HRTF. With this, I thank you for your attention, and I'm happy to answer any questions.
So do we have questions from the audience?
Could you go back one step on the qualitative attributes, not the externalization?
Yeah.
One. There's one before that.
Maybe.
One before.
Okay, it's coloration, wasn't it?
Yeah.
Okay.
Yeah.
Got it. Okay. And then you followed on with the. That's it. Have to digest. Fine. That was just a matter of information.
Yeah.
Got it.
Yeah. Sorry. In my computer, they actually are high resolution, but I think compressed when I moved it to this PC.
Is there any question from the attendees online? If you want, you can just write in the chat or on the Q&A, or let me know, and I can also switch on your microphone if you want to say something. Was head X-tracking included in this?
Yeah. So actually, so the sound localization task was static. So I was tracking that they don't move their head, but then in the qualitative test, it was dynamic, and they could explore actually the whole scene and kind of move the source around, and which kind of also is interesting. It kind of made interesting observations, because basically people told me that then the rating depends on actually which direction they kind of rate. So I kind of wanted to include to be inclusive of, people choose for themselves what they care and so where they explore, but then that meant that actually the HRTFs are so many directions and so many sort of different cues, so that depending on where you move the sound source, you might have a slightly different, you might be biased to rate it slightly differently. So kind of another complexity in understanding the match of HRTFs.
Any other question from online? No. Oh, cool. The person who asked the question said many thanks for the answer, and before he said also thank you very much for the presentation. Okay, cool. Then I guess we can stay in the same domain, and we have Ludovic talking about his work on HRTF personalization. Yeah, perfect. I'm gonna leave the microphone here. I'll pick it up later. Thanks.
Okay. Yeah. I hope you can hear me well. So I'm Ludovic Pirard. I'm from Belgium. I'm in my second year of PhD here at Imperial College London, and I'm part of the audio experience design team led by Lorenzo Piccinelli, Professor Lorenzo Piccinelli, my supervisor. And yeah, my research is into spatial audio and to look at individual localization cues and how accessible can we make them for, let's say, an end user that doesn't know anything about HRTF or spatial audio, but still want a good spatial audio experience and a good perception, let's say. So yeah, let's give a bit of background, but thanks to Rapolas, you know a bit more about what does our brain use to hear spatially. So we basically rely on intrusive cues that we learned like to perceive the world of sound around us. And we learned that in the early stage of human life, and then it's refined along the years. And we use specifically binaural cues, so differences of level and time between both ears, so ITDs and IADs. But when the sound source is right in front of you or above you or behind you in the medium plane, then there's no differences in time and levels between the ears. So your brain is starting to depend on monaural cues for each ear, which are the frequency effect of our morphology, so head, torso, and ears, and how it affects the sound around us and how we perceive it. And these are represented by head-related transfer functions, so HRTF. I'm going to also use that word quite a lot for this presentation. But yeah, let me give you a bit more details on HRTF. So head-related transfer functions, they are spatial cues, so different acoustic filter for specific positions. They are good for binaural rendering, so spatial audio using headphones, because we can apply these filters to the left and right channels of the headphones to trick your brain into thinking that a sound is coming from a specific direction. So here you can see ILDs and ITDs, and then on the right you can see different monaural cues depending on the elevation, and you can see that it varies with different elevation angles, and that's what your brain is using to locate in the elevation plane. So it all depends on the morphology of your ears, head, and torso, and it's always different between human beings. We have different head shapes and different pinna morphology. So my cues are not going to work for you if you have a different morphology, which is always the case. And it has been proven that using generic cues, so like an average set of cues, can lead into lack of localization accuracy, lack of externalization, and leads to front-back confusions. So it's nice to make them individual, of course, but how do you do that? You have different techniques. So the traditional method is to measure them acoustically, like Rapolas explained before, where we place microphones inside your ears, and then we play frequency sweeps with a loudspeaker array for all the positions that we want and that we can measure. And so that's enabled us to capture your HRTF. But of course, it needs some specialized equipment and acoustic expertise, and it poses some accessibility challenges, of course. So another solution would be looking at a higher resolution 3D model or 3D scan. So you can scan your morphology, head and ears and torso with a high resolution 3D scanner, and then use that mesh, that 3D model of yourself to numerically synthesize HRTF using boundary element methods. But of course, who has a 3D scanner at home? So it's not very accessible, and it's quite computational expensive. So still restrict their applicability. And what I wanted to explore is photogrammetry reconstruction. So basically using images of an individual to be able to reconstruct a 3D mesh, and then use that 3D mesh in the same way as I would use a mesh from a high resolution scanner to then synthesize an HRTF. But of course, photogrammetry reconstruction and using only images have several limitations, especially on the resolution of the mesh and the morphology details of the ears. But it still gives us quite possibly an accessible way to have individual cues, specifically for an end user that can use his smartphone to take pictures of head and ears from home, let's say. But of course, you're going to say, well, there's plenty other individualization methods that have been explored in the past and in research and different published papers in different journals, but they're not really accessible anyway. So there are different methods that have been done before in the past with machine learning is to look at HRTF interpolation using sparse acoustic measurements. So you have a few acoustic measurements that you've done, and then you interpolate to obtain a full HRTF. But you still need the acoustic measurements. So you need the microphones and loudspeakers. You can do that using GAN, CNN, plenty different AI methods. Or you can go for the approach of anthropometric distances, which are anthropometric measurements of your ears and head. So you can measure them yourself or ask someone to measure them and provide them in order to obtain kind of a personalized HRTF. So you can do anthropometry matching if someone in an existing data set has the same kind of morphology or the anthropometric measurement as you. But you can also do some HRTF adaptation or prediction in different ways. Or you can also use some binaural parametric models, plenty of different ways. But at the end, it always requires either measurement, acoustic measurements, or precise measurements of your morphology, images, as well as 3D scan. So it's not really accessible. There's none a magic solution to just provide your images or a simple input data and obtain a good, let's say, HRTF. So my question is, for my research, is it possible to compute an individual HRTF only using images? And for that, I've decided to design a pipeline, try to implement it, and see how far I can go into using only images of a subject and obtain a rather good or good enough HRTF. So about the methodology, what I want to do is obtain an HRTF from photogrammetry reconstruction mesh, reconstructed mesh. So I start with the photogrammetry, so basically images, and then I compute low resolution 3D head mesh using off-the-shelf tools, photogrammetry reconstruction softwares like Apple Photogrammetry API or Reality Capture. And once I have this mesh, I can divide it into two meshes, one with the left ear and one with the right ear. So two different mesh. It's quite common to do that for acoustic simulation. And you do that by doing a lot of mesh scaling, rotation, beheading. So it's kind of a few processing steps from the 3D mesh. And then from these two meshes, you can obtain a left and right HRTF using the famous tool Mesh to HRTF. And then you can combine those two HRTF and obtain a final sofa file of the individual HRTF. So it's quite a nice pipeline to be able to obtain a sofa file from only using images, but then of course you have to evaluate the end product that you obtain. So how do you evaluate an HRTF? And that's the first thing I've evaluated, like the end product, because you could evaluate the pipeline step by step, but I wanted to focus on the HRTF itself since it's what you use to perceive audio in a spatial way. So you can look at the numerical evaluation, so variation in ITDs and IIDs, as we saw before, looking also at the log spectral distortion, so seeing differences in the frequency domain between different location. Or also you could use auditory models with the auditory modeling toolbox, like Rapolas used the Birmingham model. And then, of course, an interesting thing is to do a perceptual evaluation with a listening test. So I'm going to go over this quite quickly since I don't have hours to talk about the evaluation. But yeah, let's go into different steps. But first, I'm just going to mention the data that I'm using, which is the Sonicom dataset. So Sonicom is a European collaboration, and the Sonicom dataset contains more than 350 subjects. We're collecting it here at Imperial College with the audio experience design team, and it contains for each subject HRTF acoustic measurement. It contains also a high resolution scan, so a high resolution mesh, and it also contains depth and RGB photographs, and more precisely 72 images, so one image every 5 degrees around the subject. So that's kind of the perfect data set for me because I have pictures, I have high resolution scans and meshes, and also I have a kind of a ground truth code measured HRTF, so I can compare my result with that. And yeah, let's dive into the photogrammetry reconstruction. So maybe you don't know what photogrammetry reconstruction is. So basically, it's using overlapping images to then identify common features using structure from motion. It's quite a complex thing, which I didn't dig into since it's not really audio. But yeah, it's working quite well. It's computing spare point clouds to then condense it in a one main point cloud, and then computing vertices, edges, and faces to obtain at the end a 3D mesh of an individual. And I did that for 120 subjects, sorry. And then we're going to look at the result of the reconstruction quite quickly. So on the left, you will always see the high resolution scan processed by Katarina Poole from our team. She processed the high resolution scan, and this is what you can see. And on the right is the result of the photogrammetry reconstruction. So that's the mesh obtained only using images. So you can see that overall, you can kind of see the good facial detail. So the overall reconstruction is quite good. You can see that it's a human head that has ears, eyes, and everything. But then when you look closer at the ear, of course, it's lacking in ear morphology details, as you can see on the right here, compared to a high resolution scan that we do when we collect the data. And then left ear, yeah, similar thing. But even if the quality of the reconstruction and the detail in the pinna is not perfect, I just decided to go forward with these meshes to see what HRTF can we obtain and how good is it without having to do any AI training or optimization of this step and using simple off-the-shelf, well, quite complex still tools. And yeah, then comes the acoustic simulation using the meshes. So using mesh to HRTF. How does it work? Quite quickly, you use the photogrammetry reconstructed mesh, PR mesh, and then you modify it. So you behead it, you align it, and you scale it. So it's like ready for the simulation. And then you use mesh to HRTF, again, using boundary elements methods to numerically synthesize an HRTF. And you obtain an acoustically, simulated, so a synthetic, let's say, HRTF. But of course, it seemed very easy on the slides and on the presentation, but it's not that easy to implement, and it requires a lot of power. So you need a high performance computer, which again is going to be maybe a limitation in the future. But still, it worked, and I managed to obtain 120 HRTF, and that gave me some data to analyze, since it's HRTF obtained kind of only using images as input data. And now we can look quickly at the numerical evaluation. I don't know how much time I have left, but basically I looked at the variation in ITDs, IIDs, and log spectral distortion using the spatial audio metrics toolbox designed by Katarina Poole. And yeah, what I decided to do for my analysis is to compare the obtained HRTF in red. You can see the PR synthetic HRTF with different conditions, with different HRTF that we had for the subjects. So for example, Katarina also computed HRTF from the high resolution scans that we have. So using the high resolution mesh. So these are the blue HRTF, or the blue results. And then you can see also the KEMA HRTF and then a randomly selected measured HRTF within the Sonicom dataset, which is always different between the individuals. And yeah, that's the different conditions I wanted to analyze compared to a measured HRTF for all the different subjects. And you can see that the result is okay, but not as good as it could be. So the photogrammetry synthetic HRTF are performing quite well, but in the ITDs and ILDs, but not the best in ILDs and LSD. But it's a baseline, so it's obtaining these HRTF with not a perfect mesh. But at least it's not that far. I was expecting much worse. And from that, I decided to then go forward with more analysis on these HRTF. So then again, looking simply at the spectra, we can see on the top row a measured HRTF for one subject on the azimuth plane, with the x-axis being the frequency. So it's basically how we look at HRTF, let's say. And on the bottom row, you can see the photogrammetry HRTF, and you can see that it's missing fine details. The overall reconstruction, it's looking kind of an HRTF, but it's not as detailed as a measured one, of course. Sorry for if the scaling is not the same, but you get the general picture, I guess. And then on the elevation plane, you can see that there's clearly nothing there, or you can kind of see some patterns, but not as good as some notches that you can see on the measured HRTF, like these small notches. Anyway, it clearly shows that it's missing the pinna, let's say, morphology details, and it doesn't really say anything because it's just an image. So then I decided to use auditory models, similar to Rapolas did with a Birmingham model and the Baumgartner models, which are two auditory models that are used in, let's say, localization, a representation of how a human would be able to perform and in the localization test. And if I quickly look at the results, I decided to show you the quadrant error, so a deviation of 90 degrees, comparing the two models. So Baumgartner 2014 on the left and Baramelli 2023 on the right. And basically, when using these auditory models, you have to provide a template and then you have to provide a target. What I decided to do is always use for all the different individuals the template being the measured HRTF as kind of the reference cues, and then evaluating the different targets with the same conditions that I showed you earlier, looking at the measured, the 3D scan synthetic, the photogrammetry synthetic, KEMA, and then random. And what we can see is that the measured HRTF is performing really well, but of course, it's because I'm using the same target and template, but it gives us kind of a reference. And then we can see that the other conditions are showing that the error is quite high, because it goes quite close to 50% quadrant error, which basically means that you are guessing randomly. And so if it's really close to 50%, it means that it's quite bad. But it's only auditory models, and it might not really reflect the reality of these cues. As we can see, like the KEMA is performing similarly to both synthetic conditions, and we can have a hint on seeing that the random is performing better than the other conditions. Anyway, let's dive quickly into the next step, which is using real human beings to evaluate these cues in a localization test down in virtual reality. So I basically used the exact same test that Rapolas designed. I just decided to change the conditions to evaluate my HRTF, but I reused the same environment and very similar stuff. So you have a loudspeaker familiarization phase where the individual train on localizing with loudspeakers, and then you have 3 blocks of 99 trials using binaural rendering. So you're basically evaluating the HRTF on these 3 blocks of 99 trials. The 3 conditions I decided to go forward with is the individual measured HRTF, the individual photogrammetry reconstructed HRTF, let's say, and the random non-individual measured HRTF. which is different again for each individual. It's not always the same one. And then using 33 pre-selected source position, and everything is randomized between the trials. So all the source order and conditions are randomized, so the subject cannot guess which HRTF is being used to render the stimuli, and which position is going to be with. So it's using a Unity environment with a MetaQuest 3, and the stimuli is described here on the slide, but it's basically like a like sound. But yeah, it's described in Rapolas paper in a much better way. So if we quickly look at the results, so you can see in yellow again is the measured one, the red is the HRTF obtained from photogrammetry, and then the random is in green, and you can see 4 different columns. The first one is the great circle error, so kind of the global localization accuracy on both planes. And then the second row is the azimuth plane, so the lateral accuracy. And then third row is the median plane, so elevation. And then the fourth column is just the front-back confusion rate. So how much do we are we confused between front and back? And yeah, overall, we can see that the HRTF I computed are not performing really well. It's quite of the worst for kind of all the metrics, except for the azimuth plane. And I guess it's because of the good reconstruction of the ITDs and ILDs, kind of matching the head size. But then you can clearly see that it's performing worse than a randomly measured, selected HRTF within the data set. So at the moment, my pipeline is more like a baseline, because at the moment, choosing a random one within a data set gives you a better localization, localization results. And so this is kind of a baseline to be able to later on in the future optimize the pipeline and try to be between a measured HRTF and a random one. But we were quite surprised looking at the results of the localization test to see how close a random HRTF is to a measured HRTF. And yeah, this was maybe not expected at the beginning, but it was interesting to find that it might be actually later on hard for me to be able to be between these two conditions, as in most kind of metrics, the significance difference is not really high. So yeah, I'm trying to publish this data hopefully in a paper, so you might want to look at them later on. And yeah, to conclude my work, looking at the feasibility of this pipeline, it's possible to use photogrammetry reconstruction and mesh to HRTF to compute individual HRTF, let's say. And it's offering kind of an accessible alternative to traditional acquisition methods, as if it works, you only need images, but it has its limitations at the moment. Well, looking at the results, it's looking at a good overall reconstruction of the binaural cues, but then looking at the frequency domain in the differences, you can see a high spectral distortion, especially above like 12 kilohertz, which might be due to the simulation as well, the acoustic simulation, compared to the measurements. You see in auditory models that the quadrant error is quite high, and all of that with the perceptual evaluation, with the numerical evaluation indicates that there's a limitation in capturing the fine details of the pinna. But then the perceptual evaluation insights are, again, it was quite a surprise to obtain similar performances between random and measured HRTF. And we can see that we obtain a reduced elevation accuracy and higher front-back confusion using these computed HRTF. And also I wanted to mention that the HRTF I computed are missing a torso, so there's only the head and ears. There's no torso in the simulation compared to the measured one, and more specifically the random one, where it's measured in the same room and it has all the impact of the human being. Even if it's a different human being sitting on the chair and being measured, there's still all these common components compared to the synthetic HRTF. So that's why as well it might perform not well. But yeah, all of these analysis that I've done during my first year is kind of giving me goals to try to achieve a better pipeline, to try to beat a randomly selected HRTF, and good metrics, plenty of different metrics to go on after that and try to optimize the pipeline to make accessible, good individual HRTF. So yeah, thank you so much for listening. And if you've got any questions, I'm really happy to answer to them. Thank you.
Thank you very much. So let's get a microphone. Do we have any question here from the audience? Yes.
This is kind of a question for both you and Rapolas, actually. But essentially, together you kind of have a big data set now, or fairly sizable data set of different HRTFs and then perceptual responses to each of those HRTFs. Do you know if anyone's thought it worthwhile to kind of try and derive some kind of mapping between like the numerical or signal level distortions to a HRTF and like the change in the perceptual response, and like whether anyone has tried to do some kind of, would it even be worthwhile, or like, do you think the response changes would be so individual that it wouldn't be capturable by some kind of machine learning process? I'm just thinking, like, you know, if you could sort of, if you fed something a vector of features based on differences between the HRTFs, then you're saying, well, you've got this frequency region that has this difference, and then we see across like most people that leads to this change.
Yeah, definitely. For me, the goal after this like first year of using different metrics to evaluate an HRTF and then doing a localization test and seeing the impact in the perceptual evaluation, it's kind of the next step into combining what you see on the localization test and how it's affected by what you see in the numerical analysis. So variation in ITDs, ILDs, and LSD. So kind of just the numerical evaluation. How does that affect the localization test? And how can it be later on used to optimize models to try to create a good, let's say, AI model that is going to use a different loss function to reduce these differences to output a better, let's say, set of cues, kind of. So combining these metrics are, I think, a really interesting thing to explore.
Yeah, I mean, I agree that it's probably theoretically possible. Then the question, of course, is whether it's enough data, because I mean, at the end of the day, it's hard to get to quite a substantial amount of localization responses, and they are quite varied. Like, people do perform localization actually quite poorly in a way. Like, unless they're trained, the localization performances are not that great. So it's like question of reliability of the data and stuff, but it's definitely a attempt. I mean, it would be interesting. I started doing some pooling of, like, because I've run this localization test over time, and it would be interesting maybe to combine these different times we did the same test with different people and different HRTFs to see the differences here.
Thank you. We have a question online from Francisco Bernardo. Assuming that you might go with deep learning methods in the future, would you be mapping full meshes to measure the HRTFs for each data point in the model training dataset? What is the size of a mesh in memory?
Yeah, exactly. That's a very good question. And when looking at the pipeline, if I can just go back to this slide quickly, you can kind of think of optimizing the pipeline at different steps. And where do you start? Because, sorry, just gotta map all that. You could think of a deep learning model with let's say, a black box, a magic box, where you train the model, you give just the images, and you train that model on having the input as images and the target as measured HRTF. And you could have a huge black box where you just feed the images and obtain an HRTF. Just the problem of that when I approach this pipeline is thinking, well, if I do this and I obtain a model, I will just have no idea what it's doing, because it's going to be like all internal, and it's going to be this magic algorithm that might only work for our data set. So kind of the background that we have in the images, and not being able to rely on the true individual morphological data between the participants. So yeah, what I think I'm going to do first with deep learning is to use the synthetic HRTF that I've obtained after the acoustic simulation and have kind of a model that is training from synthetic HRTF as input and then a target being a measured one. So it's going to become a refinement model to learn how to refine the output of the acoustic simulation to then obtain something that is closer to a measured HRTF. Because if I want to start with the meshes, meshes is quite large. It's like, let's say, 300 to 400 megabytes, so nearly half a gigabyte. So it's just massive for a network. And so I don't want to dig into that yet, since I want to stay in audio. And I think I've spent enough time in trying to get good meshes from the images I had and trying to use the tools that are available, like Mesh to HRTF, to obtain an HRTF. And I want to stay a bit more in the HRTF domain first to see if I can obtain better results. And then maybe later on, if it's needed, going back step by step to more of the kind of computer vision side of the project.
A follow-up question is, so your synthetic data would be images and not meshes?
The synthetic data is going to be the HRTF obtained with the acoustic simulation using the meshes that I have now. So in this presentation, I've evaluated the synthetic HRTF that I have, but I also have the measured HRTF for each individual. So in total, I have a lot of different pairs of synthetic HRTF and measured HRTF, which I can use to train a neural network.
Yeah. Okay, we have Cory, thank you. There is another question, but we need to be very fast in the response because we need to move forward. But
of course,
great to see this research from both presenters. Thanks for sharing. Regarding the perceptual tests, any thought on the potential contribution of A, a playback device, for example, a headphone type, etc., and B, polar dispersion of source in the simulation rather than just a mono-anechoic source? On the playback device, you want to?
Yeah, the headphones kind of.
Yeah.
Yes, there will be an effect. I mean, I think in my case, actually, I also tried with headphone compensation and not. I mean, they're all kind of like static filters, so there will be potentially some effect, but potentially you kind of learn fast to kind of just localize in that environment. But of course, we don't get the localization with individual HRTF binaurally as good as the one that we have with loudspeakers in this test. I mean, we are not kind of trying to optimize like our engine to kind of be as accurate as possible, but there's definitely some improvement to be done on the rendering of it.
Yeah, just a quick mention. In general, participants are saying that or in my case, they were saying that it was quite internalized, that it was hard to externalize the sound source. And I think that's due because we're only using the direct path convolution with the HRTF and the stimuli. So there's no reverb. But yeah, that's also something that affects the perception of the individuals. Yeah.
And then it was like, ideally you want, I guess, more authentic reproduction with reverb, but then how to render individual reverb then becomes less of another issue.
Yeah, then you're assessing more the reverb than the HRTF as well. So it's like, yeah, it gets more complex.
Thank you very much. So, well, thanks for these first two. Then we have William from Birmingham, and you're going to talk about violin and musical interfaces and so something a bit different.
Yeah. Okay.
Brilliant.
Nice.
We can leave this here. And to you.
So my name is Will, and I'm a PhD student from Birmingham City University, and the title of my research is Computational Analysis of Style in Violin Performance. So I'm just going to talk through some of the research that I've done as part of my PhD today. So when I started out, I had this research question, which is how can computational approaches best facilitate analyses of violin performance for use in real-world teaching and learning environments? So I kind of broke this down and started thinking about violin performance and the different aspects of a performance that we have. So we have audible and gestural aspects of the performance. So we've got kind of the standard audible aspects that we would expect, so things that we can quantify through the use of MIR techniques. But then we also have these gestural aspects of performance. And we can break those down into sound-producing motions and ancillary motions. So the first are kind of integral, so these are movements of the right arm and the wrist, which produce the bow stroke. So these excite the strings and the reverberation of the instrument body. And then we've got the fingering of the left hand, which determines the pitches of the notes that are produced. And then non-technical motion is kind of more expressive, and it's less localized to those areas of the body, such as the wrist and the left hand. And so this is kind of sonically inconsequential. It's a part of the performance and it's expressive, but it's spontaneous and it doesn't affect the actual sound that we hear, or at least to the same extent. So then thinking about applications in teaching and learning environments, I took a look through the field of existing literature, and these can largely be categorized as either machine learning based or not. So these machine learning based works I found typically dealt with two classification tasks. So that's articulation classification, so the classification of specific bow strokes, so things like spiccato or legato. And then we've got level of expertise classification. So this is implementations where participants have been recorded and then labeled by their sort of, declared level of expertise, and then we're using an algorithm to infer that based on that data. We also have some non-machine learning applications cited here. So these typically focus on more kind of biomechanical analyses, so specific kind of parameters of performance and gesture specifically that we're quantifying. So things like the jerk of a bow stroke or the rotation of the bow relative to the bridge. And then thinking further about the use of these in real world environments, I thought it was pertinent to consider the types of apparatus that have been used in each implementation. So there were three main kind of buckets that I sorted these into. So we've got applications that use the Myo armband. I don't know if anyone's familiar with that, but it's like a wrist-worn kind of interface that has an IMU sensor and a number of EMG sensors. And then the Xbox Connect, which is obviously now discontinued, along with the Myo armband. So these were two consumer devices, and then we also have quite a number of implementations that used mocap devices. Specifically, a lot of these marker-based mocap systems, which obviously kind of introduce various complications, such as accessibility, affordability, and practicality of affixing markers to participants and instruments and things like that. But notably, these were the most common used in biomechanical analyses. So these analyses that we're looking at kind of these gestural parameters tended to make use of these more expensive and more specialized pieces of equipment. So considering that and kind of the some of the barriers that those systems impose, I set about developing my own recording method. So I developed a recording method for the Apple Watch that logs the IMU sensor data and 44 kilohertz audio simultaneously. So the theory behind this was that we were recording obviously the movement of the bow stroke on the performer's wrist, and then also the sound simultaneously. So you can see here we've got one axis of the gyroscopic data. We did record all 6 axes of the gyroscopic data. And then we've got the concurrent audio that's recorded alongside that. And you can see that we've segmented this using an onset detection algorithm. We use the MADMON onset detection algorithm specifically. And then using the gradient of that gyroscopic Y data, we use that to infer the direction of that bow stroke, and obviously color-coded kind of appropriately. So as part of this, I recorded 10 participants from our undergraduate body of violin students at the Conservatoire in Birmingham. And they were recorded performing a series of scales and also short repertoire excerpts. So using this data, I first set about assessing the utility of the interface that I developed alongside a perceived sort of benchmark technology. So that was the MIO, given the precedent of this device's use in prior works. And we found in an early fusion classification task, so where we concatenate the input features prior to inputting into the model, we found comparable accuracies in that implementation, suggesting that there was a similar sort of utility of this interface to the MIO, which has been used in a lot of prior analyses. And using that, we were able to perform participant recognition and articulation recognition, so indicating that there's some performer idiosyncrasy that is quantifiable in participant performance. And then obviously also that we've got the ability using this technology to actually detect the specific bow strokes that have been played at any one time. And then a later development of this, I used intermediate fusion networks, so where we've got a concatenation that's occurring within the actual network itself, within the hidden layers. So we have these two kind of separate subnetworks that we then concatenate the outputs of before feeding to the output of the model. And we found some improvements using this this technique. We investigated kind of interchangeable layers. So there's B layers here. We kind of swapped around with various combinations, so CNN layers and GRU layers and things like that. And what we found was that essentially this wasn't always a reliable predictor of model accuracy. So you would anticipate maybe that by introducing another modality that we would get at least kind of equivalent accuracy, but we found that this wasn't the case. And so we can't always assume that that would be the case. But back to the research question. Again, I kind of found myself faced with this question of how is this applicable in teaching and learning environments? So we know that performers are kind of, there's this degree of quantitative idiosyncrasy that manifests in performance. And we know that we can, that we can capture kind of these differences in articulation that manifest during performance. But how can we apply this in teaching and learning environments? So I set about investigating the data further, and that's when I started with these kind of performance visualizations. So you can see here we've got kind of a Melodyne-inspired piano roll plot that I put together. So you can see that we've got these segments of audio here that are kind of overlaid with these target regions. So based on the score, the target tempo that performers were requested to kind of maintain. And you can see, so there's a temporal trend there. Obviously, there's this accumulated error that arises when participants play slower on average than the target tempo, or faster on average in this case, sorry. And we can't see quite as clearly from that one. We can see pitch accuracy, but we can't see tonality to the same extent as we can in this bottom plot. So this is showing the tuning in sense of individual notes, those individual note segments. And we can kind of infer a tendency from this. We can see that most of those fall above that midpoint, suggesting that this performer specifically in this take had a tendency to play down notes slightly sharper than the target tonality. But obviously we can't necessarily extrapolate that across to kind of multiple takes or music of different content. We see another example here. So this is a repertoire excerpt. It's actually Happy Birthday. But we can see, for example, we've got this target region here that's being missed on the y-axis. So obviously a pitch inaccuracy, and then we can see these areas of kind of temporal inaccuracy, which obviously may be the result of expressive sort of timings, things like that. But in this instance, kind of portrayed as a deviation from a score that was provided. But as I mentioned earlier, from those kind of depictions, we can kind of draw these conclusions about specific takes, and we can sort of visualize things to some extent, but this doesn't tell us a huge amount about how performers tend to play on average. so this is a distribution plot of temporal accuracy of individual participants in, I believe, the G major condition. So playing a G major scale, you can see that we've got the three different shades, so they denote a specific take. And what we're essentially doing is kind of condensing those sort of note durations into these KDE plots. And so we can see some kind of habits that emerge when performers were playing these scales. So you can see, for example, that on average, these blue kind of arcs at the bottom are slightly to the left, whereas the red ones are slightly to the right. And obviously that depicts that participants on average were playing their up bows slightly faster than their down bows. And then obviously we can see as well in the staccato condition, those arcs are much sort of wider, which indicates that there was lesser temporal precision in the staccato condition. So these kind of short, choppy notes than there was in the legato condition. And if we kind of inspected this further, we'd be able to see the differences between specific takes and kind of changes over time on a take basis. And then I did the same for tonality as well. So looking at tonal habits that performers have. And we see here kind of fewer factors come into play. So we can see that performer tonality, or the precision of performer tonality, is quite idiosyncratic, but it's also quite consistent across bow direction and articulation conditions. So we can see there's not too much of a difference sort of between those two when those two sort of factors come into play. And then obviously we've kind of visualized these, but we've not actually, up until this point, we've not actually kind of quantified those trends specifically. So I set about doing some statistical testing. So as I said, we can see that up bows are typically shorter in duration than down bows. This was a cross-participant trend that emerged. We found significance in this instance. We also found that staccato notes were typically shorter in duration than legato notes. Again, we found that this was significant. We found that staccato notes were less precise tonally and temporally, but the influence of bow direction towards tonal and temporal variance was insignificant. So that was kind of these plots here that I was talking about, how you don't see that same influence across those conditions. We also found something that's not as kind of apparent from those graphs specifically, that there was a positive correlation between performers' effective tempo and their tonal variance. So effectively, the performers that played faster on average had less tonal precision when they were performing. And we found that this correlation specifically was weaker in legato instances than it was in staccato instances. So when playing staccato, that correlation is kind of more pronounced, and it's a more reliable sort of predictor of habits in tonality. We did observe specific differences between note finger tonal variances. So thinking about these kinds of tonal distributions here, I kind of binned them by note fingers. When that was the case, we did see that there was a significant difference in each instance, but these weren't kind of consistent across the two scale conditions. So effectively, although when playing one scale, for example, maybe a first finger note was on average most tonally accurate, this wasn't the case when they were playing the D major scale. So yeah, I've got a short recording, an example recording of one of these participants here. So this was one of the repertoire excerpts that was recorded. I should clarify that the recording is not it's not online recording, it's offline. So the data is basically logged and then it's kind of sent across to the phone from the watch when recording ceases. So it's not necessarily as it was being depicted here where the audio is actually being transmitted and plotted in real time. But yeah, that was my presentation. Thank you for listening. If you've got any questions, I'd be happy to answer them.
Thank you very much. Do we have questions from the audience? Yes.
Thank you for your presentation. Really interesting stuff. I was wondering, the app on the watch, you designed it.
Yeah.
Yeah.
It's just a single button interface, and the idea was that it was intended to be kind of as simple to use as possible. So you just press the button, it starts recording. You press the button again, and it stops.
Nice. And is it available? Like, is it accessible?
It's not. We've not published it on the App Store.
Okay.
But yeah.
If I contact you, I could get the app as well to provide.
Yeah, you could send it over. It's a bit of a mess, to be honest. Kind of the back end of it, but yeah, you could send it over.
Okay, so it's possible. Kind of.
Yeah.
Okay, nice. Thank you.
It's probably a simple answer to this, but as the bow draws away from the string, the fiddle, and the sound, the level and spectrum are going to change. So is there some sort of compensation or just analysis of the fact that the sound is very different as you're a different part of the stroke? If your watch is much further away,
proximity effect.
The watch is not static.
Yeah, that wasn't something that we kind of corrected necessarily after recording. We did a few trial recordings initially, and we're quite sort of pleasantly surprised actually with the quality of the audio. And we didn't kind of test this in any official way, but we didn't notice that proximity effect sort of was perceivably sort of different. But yeah, maybe something to look into further.
There's probably a little bit of investigation that could be done to just check a static recording and of a watch and at the same simultaneous with.
Yeah. So when we did the Mayo comparison initially with the classifications, so I developed a recording method actually both for the Mayo and for the Apple Watch to facilitate that performance. And the Mayo recording method, because they don't have an internal microphone, we used a freestanding DPA. So we did have that comparison, and in that instance, we found that the freestanding DPA didn't offer kind of enhanced accuracy during classification, but obviously when we're looking at things like tonality and things like
right.
pitch, that has
Follow. Thank you.
Thank you. We have another question from here. Sorry, here we go.
Thank you. Nice presentation. Could you elaborate a little bit further on you have a fusion network for the audio and the view data?
Yeah.
Yes.
This one. Yeah.
So that's how you're using a neural network to fuse both the IMU stream and the audio stream.
Yeah. So during the first instance, what we basically had was these kind of slices of IMU data, raw IMU data that have been normalized and sort of segmented. And we kind of overlaid that or concatenated it with the audio features that we derived. So we derived MFCCs, delta MFCCs, and chromas. And then we basically had in this kind of matrix these sort of vertical slices that have all of that, and then fed that into a single input network initially when we were doing the comparison to Mayo. In the later study, what we had was these individual subnetworks. So we had the IMU data going into one subnetwork, and then the audio features going into the other subnetwork.
So what is the output of that network exactly?
So it would be a classification output. It'd be the same as the single input networks, except we've got this concatenation that's occurring kind of just before that final dense layer.
Okay, cool. what are you going to do with the insights that you got with this finding in terms of application to violin pedagogy?
So within the thesis, I've been discussing it within the context of pedagogy. It's something I know I've not touched on a huge amount here, but I've looked at kind of 4 different violin pedagogies. The most prominent, I think it's fair to say. And I've been kind of assessing my findings against that because we haven't been able to conduct kind of a longitudinal study or like an A/B comparison with the number of students that we've got at the conservatoire. So that's kind of the metric that I've been using to assess it. Obviously, more of a sort of a qualitative assessment, I suppose. But I think it's one of the things that I've tried to maintain during my research is an appreciation for the extent to which this is a qualitative field, essentially, that I'm studying, although we're applying quantitative means. So I think, yeah. I don't know, does that answer your question? Sorry, sorry.
Thank you. We have a question online. Fascinating. Thanks for the presentation. Have you had any feedback from teachers and students so far?
Unofficially, yeah. I've not. I mean, during recording, I think it's important to acknowledge there was some skepticism that it was met with from participants. And again, I think a lot of that is due to this application of quantitative techniques in a qualitative domain. And that's one of the reasons that I kind of framed this research the way that I have within the thesis, assessing it against that benchmark. Yeah, I think it's fair to say there's some sort of trepidation. It's faced by, or that's, that I've encountered when sort of approaching the subject with teachers, but also I found that instructors on the other sort of side of the coin have been quite enthusiastic and quite, yeah, I think it's quite polarizing, perhaps, but yeah.
Thank you very much. So I guess we have no more questions. So one thing that I forgot to mention before, Steve actually asked me to remind everybody that if you're an AES member, there are the elections for the UK panel. So please do vote. And thank you everyone for attendance online and not, and in present, and to the presenters again. And I guess we'll see each other at the next AES meeting. Thank you.